Useful power is not delivered through the conductors themselves. Power delivery in a transmission line takes place entirely via the electric and magnetic fields. Use coaxial transmission line as an example. The characteristic impedance of the coaxial line is defined here. The power flow along the coaxial line is computed from the pointing vector, as shown here.
Another good example is the light-year-long wire problem. A batter's cathode is connected to a switch that is connected to one end of a copper wire. The wire is totally a light-year long, and it loops back in the middle. The separation between two halves is 1 meter. The copper wire is then connected to a light bulb and back to the battery anode. Assume turning on the switch takes no time, and the light bulb is turned on whenever any small voltage is applied to it. The light bulb will turn on in approximately 3.33 nanoseconds. It does not take a year. It does not take half a year. It takes billionths of a second. Let's break down the exact calculation and the physical reality of why this happens. 1. The calculation. In your setup, the switch and the light bulb are physically separated by 1 meter of space across the two halves of the wire loop. When you close the switch, you are not just pushing electrons down a pipe, you are creating a sudden disturbance in the electromagnetic field. This disturbance propagates outward in all directions through space at the speed of light, c. The time t it takes for that electromagnetic wave to travel the 1 meter distance d from the switch to the light bulb is t equals d over c. The speed of light is 299,792,458 meters per second. After 3.33 nanoseconds, the expanding electromagnetic wavefront hits the light bulb, induces a voltage across it, and the bulb turns on.
2. The core idea. Where does the energy flow? To truly grasp this, we have to abandon the water flowing through a pipe analogy of electricity. If you look at this through the lens of microwave engineering and wave propagation, the two halves of your incredibly long copper wire are actually forming a parallel wire transmission line.
The battery's role. A battery does not simply spit out electrons. It creates an electric field between its anode and cathode. The switch closes. The moment the switch bridges the gap, it allows the electric field to begin propagating. Because the field is changing abruptly, a step function, it generates a changing magnetic field. The wires as guides. The copper wires are not pipes carrying the energy. They are waveguides. They act like rails that guide the electromagnetic fields through the space between and around the wires.
The pointing vector. The actual energy of the circuit flows through the empty space between the wires. This is described mathematically by the pointing vector shown here, which shows that the direction of power flow is perpendicular to both the electric and magnetic fields. When the switch closes, an expanding sphere of electromagnetic energy blasts outward at the speed of light. Because the wires are only 1 meter apart, that sphere crosses the gap and washes over the light bulb in 3.33 nanoseconds. The fields interact with the electrons in the bulb's filament, causing a tiny current to flow instantly. 3. Clarifying common confusions. Because this concept bridges basic circuit theory and advanced electrodynamics, it generates massive confusion. Let's clarify the biggest misconceptions. Confusion A. Electrons have to travel to the bulb first. Many assume that an electron has to travel from the switch all the way down the 0.5 light-year wire, loop around, and reach the bulb before it turns on. The reality, electrons move incredibly slowly. The actual drift velocity of an electron in a standard copper wire carrying a DC current is roughly a fraction of a millimeter per second. If we had to wait for an electron to physically travel 0.5 light-years, the universe might end before the bulb turned on. It is the field that moves at the speed of light, pushing the electrons that are already inside the bulb.
The circuit isn't complete until the wave reaches the end of the loop. If you trace the wires, it seems like the signal must travel 0.5 light-years to the hairpin turn and 0.5 light-years back, 1 full year, for the circuit to know it is a closed loop. The reality, at t equals 3.33 nanoseconds, the electromagnetic wave doesn't know the wire loops back a half light-year away. It just sees two parallel wires extending infinitely into the distance. It treats them as an infinite transmission line with a specific characteristic impedance. The fields bridge the 1 meter gap locally, pushing a tiny current through the bulb immediately.
Confusion C. The bulb turns on at full brightness immediately. This is the most critical nuance, and it's why your assumption,
as long as any voltage is applied, is so important. The reality, at 3.33 nanoseconds, the bulb turns on, but it will be incredibly dim. The initial wave crossing the 1-meter gap transfers only a tiny fraction of the battery's total power. For the bulb to reach its full, steady-state DC brightness, the electromagnetic wave does have to travel all the way down the 0.5 light-year wire, bounce off the end, and reflect back. It will take exactly 1 year, 0.5 years out, 0.5 years back, for the system to fully stabilize into standard DC current and for the bulb to glow at 100% brightness. Enjoying this? Smash that like button and subscribe for more RF and microwave engineering content. Drop a comment below with what you want to see next. I'm reading every single one. Let's get back to it. Thank you.